A warm welcome to this second session of live response that I wish to give to all the participants in this course. I am very happy to see that after we had the previous response session, a lot of our participants have begun to post technical questions on the discussion forum, and I am equally happy to see that there has been correspondence between participants and also correspondence between our participants and our teaching associates. So, there has been some very good technical interaction, and I wish to point out a few good questions and technical interaction that has taken place, and also respond in some detail to some of the questions that have been. So, let me now switch straight away to the interface where I am looking at some of the questions. So, I am going by order of time, that means I am going from the earliest question to the most recent question. Now, one of the questions, just around the time when I did my last response session was by Raman 111, and I am showing his post. It says, I would wish to share a little bit of the 3 questions by Professor Gadre that I could evaluate. So, basically he is talking about what happens when you add the original sinusoid to the imposter terms, to the unwanted terms. And he has tried to show that there is constructive interference at the points of sampling and destructive interference at the other points. Now, I can see that he is proceeding correctly, but I am a little sorry to see that nobody has responded to his post. So, I would like some of you to respond to this post, look at what he is doing, or share your experience of summing the imposter terms with the original sinusoid and tell us what you get. Now, I have to some extent shown you what happens, how you sum those terms. In fact, I will give you a hint of what you are going to see. What you are going to see is, as you sum more and more of those imposter terms, you will see a concentration of the sum around the points of sampling, and other than at the points of sampling, you will see a slow decay. Of course, this decay will not be monotonic, it will be oscillatory. So, there will be a lot of oscillations in between. That is because you are summing sinusoids. So, you will have a lot of oscillations in between, but those oscillations will keep dying down in amplitude, and finally you will see impulses being reached at the points of sampling. So, I have given you in some sense what you expect, but you must prove it formally by using the sum of the imposter terms. I would like more of you to respond to this post by Raman 111. In other words, I would like you to actually work out what these sums of imposter terms would give you, and then we will discuss it further. I am taking the questions which have technical content. Of course, there are questions based on the quizzes and the tests, and my teaching associates are actively looking at whatever inputs you have. As far as the quizzes and tests are concerned, I do not think I should spend time in responding to those here, but let us come to the next question, which was technical in nature. In fact, there are some very interesting posts which have come in response. So, Yadunandana says, Professor Gadre in the a priori information lecture explained that for the signal 5 cos 4t plus 5, we do not need samples at all for reconstructing the signal. Now, it has nothing to do specifically with 5 cos 4t plus 5. What I was trying to say there is that the moment you specify the signal completely, or in other words, in particular if I took a sine wave and specified the sine wave completely, there is nothing to be sampled about the signal. You know the signal in its entirety, so no sampling is required. So, what is not often brought out so clearly in some references on signals and systems is that sampling is a game between a priori information and the need to measure. So, typically it is about band limited signals or band pass signals that people talk about, and then you evolve a sampling strategy for them. But band limitedness or band pass character are one kind of a priori information. The deeper issue is that when you have a priori information, or if you have more of a priori information, you need correspondingly less of additional measurement, and sampling is a kind of measurement. So, this point was being brought out. I am very happy to see that my teaching associates have answered this very effectively Pratik has answered it, Pratik Sathe, and then my other teaching associate Sujat has also given a response, and I am also glad to see that Yadunandana has also understood what was being discussed by the teaching associate, and he has given a very correct response. He says, I want to compare this with a practical situation. So, he takes a system where we are using an analog to digital converter, and if you know exactly what you are acquiring, there is no need to sample it at all. That is correct. So, if you know exactly what you are acquiring, there is no need to acquire it. That is one way to look at it. So, and Sujat and Pratik have given a response to that. In fact, Sujat has said that in a signal generator, if you know exactly where to tune, suppose you put your knob at so many hertz of frequency or so many kilohertz of frequency in this amplitude and phase, then you know exactly what you are generating, so there is no problem. Anyway, this was a good response. Now, let us see some of the other technical questions. Well, this is of course a not so technical question, but an interesting response that I got. D cohort 1, he just started watching some of the lectures of week 4, and we talked a little bit about electronics and circuits. Now, in fact, I did that because I want to show you that you can relate a lot of what you are studying in signal systems to actual circuits and electronics. And of course, he has encouraged us to give a course on electronics. So, we will think about that. It is a very interesting suggestion. We will think about it seriously. Now, a very important question by Abhi Shah. So, which domain is best suited to see the sampling process? What aspects make time and frequency different? And how do we choose which domain is best suited for a particular situation? Elaborate with an example. Now, I had in fact given a partial response myself to the question. I had told Abhishar that if you really wish to understand which situation, which domain is better, it also has to do with the context in what you want to understand. So, I had given him the example of a fan. Now, you must have noticed that when you switch on a fan and when it rotates slowly, it seems to rotate in the correct direction. And after a while, when you start increasing its speed and you keep looking at it, it seems to actually, even if you are increasing the speeds, it seems to rotate slowly in the opposite direction. Now, this is directly a consequence of aliasing. And to understand this, it is better to use what we call the natural domain or the time domain. So, let me now put this down in terms of drawing. So, let us take for example a wheel like this, and let us put spokes on the wheel. So, from 0, 1, 2 and so on. So, I put 24 spokes on the wheel. Now, let us assume that you are causing this wheel to rotate in the anti-clockwise direction, or rather it is clockwise here, that is all, it does not matter really. Now, you see, suppose the wheel is rotating very slowly and you have fixed your gaze here. What would you see in sequence? We would see 0 followed by 23 followed by 22 and then 21, and that keeps going slowly. Now, suppose we rotate it faster. So, remember, when we fix our gaze at a point, our eyes do not look at that point continuously. In fact, our eyes in a way all the time sample, and this is why we have what is called persistence of vision. So, when a movie is recorded, you only need a certain number of frames per second, because in between those frames the eye interpolates. So, there is already sampling taking place in our visual process. So, here too in this case, if we fix our gaze at that point and we start rotating faster, maybe we will see 0 followed by, let us say, suppose you skip 2 and then see the third, so 21, skip 2 and see the third, so 18, and then skip 2 and then it comes to 15 and so on, 12 and then so on. Now, suppose we go even faster, you can go faster and faster and faster, and then you will come to a point where you see 0 followed by the one exactly opposite to 0. So, let us take that situation again. Let me show that in blue. Even faster, you see 0 followed by, let us say, 12, and then followed by 0 and 12 and so on, so you see this. So what are we seeing here? This is a point where confusion begins, because you see 0 followed by 12, followed by 0, followed by 12, and then you do not quite know whether the wheel was rotating in the direction that I have shown you or whether it was rotating in the opposite direction. In both cases you would see 0 followed by 12. So it is a point where confusion just begins. And now if you rotate the wheel even faster, so I am going to show that case in black, even faster, and I am going to write inside, we will see 0, and then all this will get skipped, all this, you will see 11 next, and then all this will get skipped and you will see 22 next. So it gives the impression that you are seeing 0 followed by a number on the right half side and then followed by a number on the left half side, and the eye would tend to feel that the wheel is rotating in the opposite direction with a lower velocity rather than in the correct direction with a higher velocity. In fact, if you go even faster, perhaps you might see 0 followed by one of the numbers here, let us say 5. So you have gone through all this between two strokes of the eye. So you have just skipped out 6 steps. So after the 24 you have skipped out 6, so you have covered 18 steps. Now you go 18 more steps here. So when it rotates like this, you are seeing 0 followed by 5, and then you go 18 more steps from 5. So you see something. So you can now visualize this. When the wheel rotates faster and faster, it actually appears to bring numbers from the opposite side as if the wheel were rotating in the opposite direction at a much lower velocity. You understand? So this is best understood in the natural domain. This is an instance of aliasing best understood in the natural domain. When would you like to understand aliasing in the frequency domain? And now I will go back to the question that Abhishar had raised. When would you like to go back to the frequency domain? When you wish to analyze non-idealities. So, I have said, so the fan rotating faster and faster I have explained here now. Now I told this is the situation B. Now the situation A is you have used a whole circuit after sampling. And I have said that there are advantages of using the time domain, there are advantages in using the frequency domain. If you use the time domain, you understand the nature of the waveform that you expect. But you are not clear what is happening in the frequency domain, what frequency components are being created, what sinusoids have come into the picture. When you go into the frequency domain, it is very difficult to visualize what waveform you can expect in that simple sample and hold circuit. But you understand what is happening, which frequencies are being brought in, which sinusoids are being brought in when you put a sinusoid into the sample and hold circuit. So the answer is that both the domains are revealing in some sense. They reveal different kinds of information, and it is by experience that one can understand which domain one should use to understand a certain phenomenon better. I am sure Abhishar might want to post a little more on the discussion forum in response to this, and I will be happy to see that. Well, I saw a question related to the magnitude response of filters, again coming from Raman 111, and I think I had answered that question. Well, in summary, the question related to when we make filters reconstruct the sample signal, what do we generally prefer in the magnitude response? Do we prefer a good gain, or do we prefer to have approximately unity gain and put the amplifier stage separately? And the answer which I gave was that a good gain is not always a primary concern. What is important is the magnitude shape and phase response. So it is a relative gain between different frequencies that is important, not the absolute gains, and I think that was understood. I also had a very interesting discussion on the windows with R Mirage, and I answered Mirage's question with some explanation of the windows. In fact, the whole subject of FIR, finite impulse response filter design, is a very rich subject in discrete time signal processing, and if we have an opportunity to build a course on digital signal processing in future, we would spend quite a lot of time discussing the whole question of designing different windows and their merits and demerits. I have given the answer in a nutshell in this post. Now, there are several questions about the exams, those I think my teaching associates are taking care of, I do not need to go into those. But I see here a very interesting question on the normalized frequency. Sandeep Unna has asked the question, why is the maximum normalized frequency less than or equal to pi? Now, you see, the pi is on the normalized angular frequency axis representative of the maximum frequency component that could be present in the original signal if you do not want aliasing, and my teaching associate Sujat has answered the question very well. I also see a very interesting question posed by Saumya Deepto Bhattacharya, and in a nutshell the question says, is it that a signal has to be limited in time or in frequency? So there are subtle points here. A signal may be unlimited in both. So the Gaussian signal, for example, is unlimited in both domains. A signal could be limited in one, but then it cannot be limited in the other. So what cannot happen is the signal is limited both in time and frequency, that is not possible. But it could be limited in one and unlimited in the other, that is possible. And then, since this question has been raised, if you evolve a measure of the spread of the signal in both the domains, in time and frequency, it can be shown by something called the uncertainty principle, that there is a fundamental limit, lower limit to the product of these spreads. The product, because you can always squeeze a signal in one domain, it expands in the other, but the product is lower bounded if the signal has finite energy. This is beyond the scope of this discussion, but I thought I will mention it at this point. Now, there was a question about digital signals and discrete signals from Dinesh Papula. You see, digital signals are discretized in both domains, in the independent variable domain and in the dependent variable domain. Discrete independent variable signals are discretized on the independent variable, but not on the dependent variable. Now, there is a very interesting question here. There is a question relating to the region of convergence. Now, Abhishar has again posed a question on the region of convergence. So, he asks, why is there no region of convergence for the Fourier transform? The Fourier transform, as my teaching associate very correctly answers, Pratik Phegde has answered the question very nicely. He said that the Fourier transform is actually a special case of the Laplace transform. So, the Fourier transform is meaningful if the Laplace transform converges on the imaginary axis for the case of continuous time, and if you are talking about discrete time, when the Z transform converges on the unit circle. So, there is no concept of region of convergence in a Fourier transform. The region of convergence needs to include a certain contour in the Laplace transform or the Z transform if the Fourier transform exists. Well, let me see, are there any other questions that we have not answered here? Well, I would certainly, please do not misunderstand if I have not answered some question. It is not because I want to ignore you or something. It is just that I might have missed some technical point which was raised. Even then I am just looking at it once to make sure that I have not missed something of importance. Well, yes, I think I believe that we have taken up most of the technical questions. Now, one general remark, I am very happy to see that all of you are participating wholeheartedly in technical discussion in this course. This is a second course in signals and systems, and I know the material is a little more difficult than the first course, and that is why discussion is even more important. So, I am looking forward to more discussion with you on the discussion forum and otherwise when you post technical questions and when you raise queries, and also answer other people's technical questions. With that, looking forward to even more enthusiastic participation from you. Thank you so much, and we will conclude this session now.